Hey folks, my name is Nathan Johnston, and welcome to the very first lecture for Introductory Linear Algebra, which is Math 2221 at Mount Allison University. In these lecture videos, I'm going to walk you through the course note PDFs that are available down below in the video description. Okay, there's going to be 12 of these course note PDFs provided throughout the semester, one for each week of the course, and each of these PDFs will be split up into 3 or 4 videos. Okay, so overall throughout the course, there's going to be somewhere between probably 40 and 50 lecture videos. Okay, so let's get to it. What is linear algebra? Up until now in your mathematical education, you've probably gotten this idea that calculus is what math is, right? Because you've taken calculus courses, you've taken pre-calculus courses, you took functions courses to prepare you for that pre-calculus course, which prepared you for that calculus course. But that's sort of a very wrong idea. Calculus is not math. Calculus is one tiny piece of math, and there are all these other pieces or branches of mathematics as well. And what linear algebra is it's the nice soft core in the center of all those pieces. It's the thing that glues them all together. It's the area of math where things work out well, and then these other branches like calculus, well, those are things, sort of extensions of linear algebra, where we tack on our ugliness on top of it. Okay, so, well, what sorts of things can we do with linear algebra? Well, one thing that we can do with linear algebra is we can do all sorts of geometry. We can answer all sorts of geometry problems. So, for example, linear algebra, it lets us compute distances between points, and it also lets us compute angles between lines. Okay, and neither of those things should seem particularly revolutionary. You hopefully know how to do both of those things already from back when you learned Pythagorean theorem and trig. But the nice thing about linear algebra is it gives a common framework for doing these things in any dimension. And in a lot of cases, it lets us avoid trigonometry altogether. Okay, what else can we do with linear algebra? Well, linear algebra, it also lets us transform geometric objects. So for example, in two-dimensional space, if we have a picture of an apple and that picture is stored on our computer in some way, and then we say, okay, well, I want to take that picture and shear it. Okay, so I sort of want to skew it in the x direction. Okay, well, in our heads, that's a very natural thing, and we can maybe even imagine what that looks like. But sort of, how do you tell the computer where each of the different pixels in this apple should go to then? Okay, and that's a calculation that you can do with linear algebra. You can apply something called a linear transformation to that apple, and it'll turn it into the skewed apple over here on the right. Okay, and then maybe we want to take that skewed apple and we want to rotate it. So again, like the problem is, okay, like I understand what that means, but how do I tell my computer where like these green pixels should now be located and where these red pixels over here should be located and this little white reflection spot in the middle, where should that be located now after I rotate it by some amount? Well, again, you apply a linear transformation to the apple, and oh great, now we get this rotated skewed apple over here. And again, that's something called a linear transformation. That's something within the realm of linear algebra. That's something that we'll learn how to do in this course. Okay, so, I mean, very related to this is computer graphics, right? Okay, so if you want to sort of represent a three-dimensional world inside a computer, like, how do you do that? How do you make the objects move? Like, what is the math that's going on there? Well, that's linear algebra, okay? Like, this three-dimensional stuff can all be encoded in linear algebra, and the movements are linear transformations, okay? And then even this problem of, okay, great, I've got all this stuff represented in 3D space. How do I sort of flatten that down onto the user's two-dimensional monitor? How do I encode this three-dimensional information in a 2D picture that the user sees? Well, again, that's a linear algebra calculation, okay? You're projecting three-dimensional space onto a two-dimensional surface. Projections are linear algebra. Again, they're linear transformations. So those are the types of things that we'll learn how to do in this course. Or rather, that's one family of types of things that we'll learn how to do in this course. So geometry is one thing, but also linear algebra is fantastic for data processing, okay? If you have very large amounts of data, okay? And this is sort of how Google got its start, okay? So, you know, the heading here is, how does Google work? Well, how did Google work? No one really knows outside of Google how Google works nowadays. They've got all sorts of stuff under the hood that's, you know, closed source now. It's sort of proprietary. But back in the day, when they first got their start, they published a paper explaining, you know, how their Google PageRank algorithm works. So how did they sort of decide, oh, these pages are probably really important pages that someone wants in their search results, and these pages down here, even though they have the same keywords, yeah, they're kind of garbage pages that the user probably doesn't care about, so we're going to rank them much lower and have them further down in the search results. How did Google do that? Okay, how did they sift through the data and determine which pages are important and which pages aren't? Okay, and what they did was they represented the internet as a graph, okay? So sort of as a little toy model here, let's imagine the internet just had 5 pages that we're calling A, B, C, D, and E. And then, we represent the links between these different pages via arrows like this, okay? So this arrow at the top here means that somewhere on page A, there's a link to page B. Okay, and similarly, this arrow over here means that page C links to page B. And hey, these double arrows down here, these mean that pages B and E both link to each other. Okay, so what Google did was they took this graph. It wasn't a graph with just 5 pages. It was a graph with billions of pages, right? Because there's tons of internet out there. And they represented it via something called a matrix. And a matrix is really nice. It's a linear algebraic object. Okay, and what it is, it's a 2-dimensional array of numbers, okay? So like this thing that we've got over here. And the way that you can turn this graph into a matrix, we're gonna see that you can do lots of things with matrices. This is only one tiny example. But what they did was they turned it into a matrix in this way. Everywhere they saw an arrow, they put a 1 in a corresponding matrix entry, okay? So because there are 5 pages in the internet here, it was a 5 by 5 matrix with each row and column corresponding to one of those pages. And here, we think of this as like the A-B entry of the matrix, okay? There's a link from A to B, so we put a 1 in the A row and B column. Similarly over here, there's a link from C to B, so we put a 1 in the C row, B column. Okay, and similarly, all of these 1s correspond to particular arrows in this graph over here. So now if you want to sort of assign an importance rating to each of the pages on the internet, one sort of naive thing that you could do is just count up the different number of links that are going into that page, right? So I mean, B would be most important because it's got 4 links coming in, and then maybe D and E are next most important because they each have 2, and then A is next most important, it has 1, and then C sucks, no one links to C, okay? But a better thing to do would be to take into account how important the pages that are linking into each page are. Okay, so rather than just saying, oh yeah, each of these 4 links in count equally, well, we would weigh this link in from page C a little bit weaker, because no one cares about page C, so they probably don't care where page C is linking to either. Okay, so it's sort of this self-referential thing, right? The importance of a page depends on the importance of the pages linking into it. Okay, so it's a chicken and egg thing. Well, how do you compute the importance of a page if you need to know the importance of a page before you're able to do that? Okay, and the answer is linear algebra. This is something called an eigenvalue problem. Okay, to sort of solve this problem and rank the pages according to importance, taking importance into account in the links here, well, you use something called eigenvalues and eigenvectors. Those sort of isolate what the important pieces of a matrix are. And we'll talk about this at the end of the course. We'll talk about how to compute eigenvalues and eigenvectors and all of the neat things that you can do with them at the end of the course. Okay, so with the introductions out of the way, let's start actually doing math. And we're going to start off by talking about vectors. Okay, I expect that a lot of you have seen vectors at least a little bit before, but we're going to go over them anyway, just to make sure that we're on a common footing. And for today's lecture, we're only going to talk about vectors in 2-dimensional space. So things like the vector 3, 1. Okay, a vector is just an ordered pair of numbers, of 2 numbers in this case. Okay, and there are all sorts of different notations that people use for vectors. So for example, when I write things, like with pen and paper, I use this notation here. I use like lowercase letters with an arrow on top, and that arrow on top indicates that it's a vector. Okay, oftentimes when I type or when, I read textbooks, I will see and use notation like this. And what I'm trying to do there is make that a bold lowercase b. Okay, so it's hard to write bold lowercase letters, bold letters in general. So I only use this notation when I type, and it's fairly common in textbooks, okay, and in written papers. Another notation that you might see in other classes, in particular in physics classes, is you might see notation like this, AB, and again, the arrow on top indicates that it's a vector, okay? And like what the AB indicates here is that, you're starting from, it's the vector going from some point to another point. So it's going from A to B. So what I mean by that is, well, we've got 2 points in 2-dimensional space here. Okay, so I've got some point A and I've got some point B. And then I can talk about a vector going between them because we can interpret each list of 2 numbers here as sort of a displacement in the x direction and displacement in the y direction. And don't worry, we're going to talk about this interpretation a lot more in a moment. Okay, but so this notation here, AB with an overline on top, we won't use this in this course, but this is all it means. It means the arrow from one point A to another point B. Okay, so how does this geometric interpretation of vectors work? Well, the entries of a vector, so for example, the numbers 3, 1 up here, the entries are 3 and 1. What those represent is how far the vector is moving or how far it points in each direction, so in the x direction and y direction. Okay. Importantly, they do not specify where that vector is located in space. Okay, so we think of these lists of 2D numbers, the geometric way of representing them is via arrows in space. Okay, so for example, the vector 3, 2, okay, what we mean by that, the geometric interpretation is it's the vector that points over 3 units in the x direction and up 2 units in the y direction. Okay, so its entries 3, 3, and 2, 2, they represent sort of how far it points in the different directions. It has nothing to do with where it's located in space, though. Okay, so in particular, this vector that I already drew, it's the same as this other vector up here, because this vector also points 3 units over to the right and 2 units up. It's located at a different point in space, but that has no effect on what vector it is. Okay? It's also the same as this vector and infinitely many others as well, right? As long as sort of the direction and length are the same, they're the same vector. Okay, and usually, okay, unless there's good reason to do otherwise, usually we position vectors so that their tail is at the origin. In other words, so that their back end is at 0, 0. So this vector here is where we would usually draw that vector, unless there's a good reason to do it otherwise. Okay, and we call this standard position. So this vector here, we say that it's in standard position, but these other two, they're not in standard position. Okay, it's not that there's anything wrong with them, it's just they're not in standard position. Okay, so really, to emphasize, vectors, they represent motion or displacement. They represent, how far you're going in one direction and how far you're going in another direction, but not where you are. Okay, so they represent motion or displacement, but not location in space. Okay, the order of coordinates matters in vectors. Okay, so the vector 2, 3 is not the same as the vector 3, 2, for example. Okay, this first one means you walk 2 units in the x direction and then 3 units in the y direction, whereas this one on the right means 3 units in the x direction and 2 units in the y direction. Okay, so order matters in vectors. There are other mathematical objects called sets where order doesn't matter. Those are not the things that we're looking at in this class. Okay, we say that 2 vectors are equal if and only if they have all the same entries in the same locations. So for example, these 2 vectors here, they have the same entries but not in the same locations. So they're not equal. Okay, the same entries have to be in the same spots for 2 vectors to equal each other. Or equivalently, we say that 2 vectors are equal if they have the same length and direction. Okay, and we don't necessarily know how to actually compute these quantities yet, but hopefully you understand what that means sort of intuitively, right? These vectors over here that I drew, these 3 vectors on the right, they're all pointing up at the same angle and they all have the same length. Okay, so they're the same vector. Okay, so vectors are equal if and only if either they have the same entries in the same spots or same length and direction. Those conditions are equivalent to each other. It's often going to be useful to talk about something called the 0 vector, which is just the vector where each entry is 0. Okay, so the vector 0, 0 is called the 0 vector, and it's denoted just by a 0 with arrow over top. Like 0, but arrow means it's a vector. All right, and one final little piece of terminology and notation here. Recall that the set of real numbers is denoted by this funky blackboard R. Well, the set of all 2-dimensional vectors is denoted by R squared, or R2. Okay, and that just means R, except, well, sort of 2 copies of R, right? There are 2 entries, and they're both coming from R. They're both real numbers. All right, so that's all just terminology and notation and boring stuff like that. Let's start doing things with vectors now, okay? What can we actually do with vectors? All right, well, the first thing that we're going to do with vectors is we're going to add them to each other, okay? We're going to take one vector, we're going to add it to another vector to get a new vector, okay? And the geometric interpretation of this, like what this operation is, you start at the tail of the first vector, you walk along it, and then now I'm at the tail of the second vector and I walk along that. Where did I end up? Describe sort of the total motion that I did, total displacement there after walking along both vectors, one after the other. Okay, so let's draw a little picture here. Okay, so I'm going to draw the vector 3, 2 to start with. I did not draw it in standard position here. It doesn't really matter, right? It's, this vector, it goes over 3 units, then up 2 units. So it's the vector 3, 2. And then what I'm going to do is I'm going to add the vector 1, 3 to it. Okay, and what I mean by that, geometrically, what that means is I'm going to place this vector 1, 3 at the end of the vector v. Okay, so I'm just sort of stacking v and w head to tail, this is called. Okay, then adding them up is the vector that goes from the tail of the first one to the head of the second one. V plus w, it's this vector that it goes all the way from the start, all the way to the end. Okay, and what it is, if you sort of count notches here, well, it goes over 1 unit, 2 units, 3 units, 4 units altogether. So its first entry is going to be 4. And then how many units does it go up? Well, it goes up 1, 2, 3, 4, 5. It goes up 5 units. So it should be the vector 4, 5. Okay, and then if you squint really hard, look at these numbers. I'm taking the vector 3, 2, and I'm adding 1, 3 to it. Well, 3 plus 1 is the first entry up here, 4. And then 2 plus 3 is the first entry up here, 5. And that makes sense, right? To get the total x displacement, just add up the individual x displacements. To get the total y displacement, just add up the individual y displacements. So all you got to do to add two vectors is just do the silly thing that you would have done, even if I didn't tell you how to do it. Just add them up entry-wise. Add up the first pieces, 3 plus 1 is 4, and add up the second pieces, 2 plus 3 is 5. Okay, but it's nice because it has a very simple algebraic formula, just entry-wise addition, but also has a nice geometric interpretation, going from, sort of combining two paths of motion from the start of the first to the end of the second. Okay, and we're going to see that over and over in this course. We're going to have sort of nice, simple algebraic formulas, but also nice, simple geometric interpretations of that formula. Okay, so that's vector addition. There's one other basic building block operation that we have to be able to do on vectors, okay, and that is something called scalar multiplication. And what scalar multiplication is it's a way of changing the length of a vector. It's a way of stretching it or shrinking it, or potentially reflecting it as well, but otherwise not changing its direction. Okay, so here's the geometric setup. Suppose that we got this vector 2, 1, and if I draw that over on the right, it looks like this. Okay, so here's the vector 2, 1. Okay, well, the vector 2 times v, well, that's just going to be the vector that points in the same direction as v, but twice as far. Okay, so 2 times v over on the right here points in the same direction, but goes twice as far in that direction. And the entries of this vector, well, they're just each twice as big. This new vector is the vector 4, 2, right? It points twice as far in the x direction and also twice as far in the y direction. Okay, so all you're doing is you multiply entry-wise, right? You multiply each of those entries by whatever scalar is out in front, 2 in this case. Okay, you can also do this with negative scalars. So for example, I can talk about the vector negative v. Okay, and you also just do this entry-wise, multiply 2 and 1 each by that negative 1 scalar that's out in front. And when you do this, you get a vector that is the same length as v itself, but now its direction is reversed. It just points, instead of up to the top right, now it points to the bottom left, sort of just rotated 180 degrees around. Okay, and you can even do this with scalars that are less than 1, or even negative and less than 1. For example, you can multiply a vector by -1/2. Again, just do it entry-wise, nothing fancy happening there. And this time, the negative sign out in front tells me, oh, the direction was flipped, and the 1/2 tells me that the length was multiplied by 1/2. Okay, so where's this going to be on the picture? Well, it's going to be pointing down to the bottom left, but half as long. Okay, so -1/2 v is this vector right here. Okay, so all of the scalar multiples of v, they're just different vectors of different lengths on this line right here. Okay. All right, so yeah, I mean, more specifically, if you just have any scalar c, then c times v is just the vector that you get if you multiply each of those entries by c. Okay, and then basically that's all we need to be able to do linear algebra. We need those two operations. You can build sort of everything else out of those two operations. So for example, if I want now to subtract two vectors from each other, well, the way I can think about that is I can think of it as the first vector plus -1 times the second vector. And then just, if I combine everything that I know, well, then v minus w, if those are two vectors, had better be v1 minus w1 and v2 minus w2. In other words, you just do it the entry-wise obvious way, just like with vector addition and scalar multiplication. Okay. This time, though, the geometric interpretation is a little bit weirder. It turns out that in this case, if you're doing vector subtraction, what you get is you get the vector from the head of the second vector to the head of the first vector, if you drew both of those vectors in standard position. So that's weird to think about. Let's draw a picture and try to explain why that is. Okay, why is vector subtraction work so weird geometrically? All right, so suppose we got these two vectors, 3, 1 and 2, 3. Then, well, the difference between them, if I just work entry-wise with that formula, you just do 3 minus 2 is 1, and 1 minus 3 is minus 2. Okay, so algebraically, it's very simple. It's exactly what you would expect. Geometrically, what is it though? Okay, so geometrically what it is, well, you draw your two starting vectors in standard position. So here are v and w starting from the origin, so in standard position, right? V was 3, 1, so, over 3 units up 1 unit, and w is 2, 3, so over 2 units up 3 units. And then I claim, this claim up here is that v minus w goes from the head of w to the head of v. So it should be this vector pointing down here. Okay, and I mean, yeah, you can convince yourself of that easily enough. This vector 1 minus 2, so over 1 unit, down 2 units. Yeah, that looks about right. Why is that happening though? Okay, like why is this a thing that's true in general? And the way to think about this is just remember that subtraction undoes addition. Right? So think about it in terms of addition instead. What I've got here is I've got a triangle where I go from w, I follow the path of w, and then I follow the path of v minus w. Well, if I do w plus v minus w, well, the two w's cancel out, I'm just left with v. Right? So this is just the addition rule sort of flipped around a little bit, right? If I add w to v minus w, then I get w plus v minus w. Oh, I just get v. I get the other side of the triangle, just like with my addition rule from earlier. Okay, great. So now we know how to add vectors, do scalar multiplication, subtract vectors. Let's do an example, okay? Let's actually compute something with this, okay? So here's sort of our first non-trivial example. Suppose that we've got a regular hexagon, okay? And it's just gonna be centered at the origin, so centered at 0, 0, and I'm gonna put one of its corners at the point 1, 0, okay? What I wanna do then is I wanna find the sum of the 6 vectors that are pointing from the center of this hexagon out to its 6 corners. Okay, so, start off by drawing a picture, right? Okay, so to make sure that you understand what the heck is actually being asked here. So first off, I'm gonna draw a hexagon. I'm told that it's a regular hexagon, and what that means is, all of the sides and angles are the same. Okay, so if this length here is 1, then these are also 1 as well, and it's regular, so sort of all of these interior angles here are 60 degrees, okay? And all of these exterior angles are 120 degrees. Okay, so we got one corner over at 1, 0, center at 0, 0. This one's going to be at minus 1, 0, and then these coordinates here are a little bit uglier, but you could find them with trig if you wanted. Okay, and now what the question's asking me is find the sum of the 6 vectors that point from its center to the corner. So I'm going to draw those vectors on here now as well. Okay, so we've got 6 vectors pointing from the center out to its 6 different corners. And we want to add those 6 vectors up. Okay. And the point that I'm trying to make with this example is that there are sort of 2 ways that you can go with almost any linear algebra problem. You can go the algebraic way or the geometric way, okay? And I know for a lot of students, you just want to try to hammer the algebraic way right away because it's sort of what you're used to. It's what we've taught you in math up until now. Okay, so let's try that. Algebraic way. Okay, the algebraic way to solve this problem is you compute the entries here, 1, 0, and then you compute the entries here and here and here and here and here, and you add them all up. Okay, the only annoying thing about doing it this way is that 4 of these points, these 4 right here, require you to use some trig or special triangles to figure out what their actual coordinates are. Okay, so this calculation will actually end up being a little bit ugly. Okay, so there's a better way, and the better way is to think about geometrically instead. Don't try to compute it algebraically with numbers, just try to solve the problem by thinking about the geometric properties of the thing that you're trying to compute. Okay, so the trick here is notice that these 6 vectors, well, they come in plus minus pairs, right? These 2 vectors, for example, are negatives of each other. If we take the negative of this vector, we get this vector. And similarly for the other vectors, right? If I take the negative of this vector, I get this one. If I multiply this vector by minus 1, I get this one. So the vectors very naturally come in pairs. And if I add up any of those plus minus pairs, I'm going to get the 0 vector, right? Because whatever the entries of this vector are, they're the negatives of the entries of that vector. It doesn't matter what their actual values are, we know that they're negatives of each other. So adding up these 2 vectors gives us a 0 vector. Adding up these 2 vectors gives us the 0 vector, and adding up those 2 vectors gives us the 0 vector. So since each pair adds up to the 0 vector, the whole sum must be the 0 vector as well. Okay, so the sum of those 6 vectors is just 0, 0. It's the 0 vector. Okay, and that's a much more elegant way to solve this problem. In particular, I mean, we didn't have to do any nasty calculations with trig, but also this method of calculation, it sort of generalizes to maybe other problems where, okay, what if I had like a 12-sided polygon or something like that? Okay, the sum's still going to be 0 for the exact same reason. Okay, you don't have to all of a sudden now do new trig calculations to figure out what the coordinates of this 12-pointed polygon are. Okay, you just know right away using the same argument that the sum would still be 0. All right, so I want to close out this lecture with one final way of thinking about v plus w and v minus w, the summing difference of two vectors, okay? And this interpretation comes from parallelograms, okay? We can think of our previous geometric interpretations of v plus w and v minus w as coming from triangles, right? If you have one side that's a vector and then another side that's a vector, then their sum is the third side of that triangle. Okay, but you can also think of this in terms of parallelograms, and we're going to see parallelograms come up over and over and over again in this course. Okay, so the way that this interpretation works is you take your two vectors v and w and you construct a parallelogram out of them, okay? So you start off with v and w in standard position. That's what these two vectors at the bottom left are. And then what you do is, well, this side of a parallelogram is the exact same as the parallel side. So if this is v, then this side is also v. Okay, and similarly, if this side is w, to make it a parallelogram, just translate w over. It's the same vector, just at a different spot. Okay, so two of the sides are w, two of the sides are v, and then, well, very naturally appearing in this parallelogram are the two diagonals. And it turns out those two diagonals, they're exactly these vectors v plus w and v minus w. So for example, if I add up v and w, what do I get? Well, one way to think of that is, I walk along v and then I walk along w, and oh, so v plus w has got to be this vector going from the origin all the way up to the tippy top there. In other words, it's the long diagonal of that parallelogram. Okay, and that's true. Okay, v plus w is one of the diagonals of the parallelogram. Okay, what about the other one? V minus w. Okay, well, that's got to go from the head of w to the head of v. Okay, so that's just the other diagonal of that parallelogram. Okay, v minus w is the other diagonal of it. All right, so that'll do it for today's class. Next class, we're going to talk about three-dimensional vectors and even vectors in higher dimensional spaces that we can't visualize. So I will see you then for that.